And for those 5 who missed it, at least they get a shorter video to watch. Only an hour instead of an hour and 15 minutes. Okay. Now, since there's still a significant number of you who, yep, still only one person down in Gulf Park. Okay, dang it. Since there's still a significant number of you who've not yet completed first homework, well, actually, are there any questions on anything, whether it's homework 1 or chapter 2 so far? What do you got? Yes. Okay, so this is the, okay. Scroll. This?
Yeah.
Okay. Yes?
I'm sorry. I can barely hear you down here. I don't know if you're further away from the microphone than usual.
I don't. Okay, I don't think I am. This been going on the whole time?
Yeah.
Okay, that's the thing you let me know about sooner. So, yeah, I mean, you can interrupt in a situation like that. It's okay. Yeah, I'm. Okay. Oh, on this panel or okay. Is it the little dial here? Okay. Now, as I turn the dial, is that helping at all, Rachel?
No, sir.
Oh.
She's gonna have to turn it off from there.
Oh, so maybe it's on your end. So I just made you louder up here.
Okay. Do I need to do something on the tablet?
Apparently, yeah, because like what I have here is there's a panel that has like a whole bunch of controls, and there's a dial to turn up the volume. I don't know if you have the same equipment down there. That would be nice, but that would make too much sense.
I should.
Okay. Well, I'll keep yakking and let me know if there's any improvement. Are you finding anything there?
Not really. Honestly, I'm scared to press too many buttons.
Can't blame you for that. Well, I could annoy everybody up here by talking louder.
Oh wait, I think I found it.
Okay, so is that helping
there
at all?
It is.
Okay, good.
There we go. Okay.
All right. Well, it's good to know because that's bound to happen again. Okay, so Jade, your question about this.
I don't know where to start on it at all.
Okay, so what you would do is first you would plug in this x naught pi over 4 into both of these, the function and the Taylor polynomial. So this plugging into here will give you your y. Plugging into this, the approximation will give you your y hat. So there's your forward error. And then as far as backward error, well, this is your true x. And then you would take your y value, your y hat, and assume that it's equal to cosine of x hat. That gives you x hat. And then you can carry it out from there. Okay. More? As your approximation, yeah, yes. Yeah, so you can think of this function P2 here, that's kind of like your f hat. Yes.
At the very end of exploration 2.1.10,
okay.
compare these estimates to relative condition number of f of x at x given by 2.1. Is that supposed to be continuation?
Wait, okay.
There's supposed to be another number after that.
Dang it. Hello? Oh, I think it's because I just changed the book that sometimes PDF doesn't show up right. Dang it. Okay. Okay. 10? Okay.
The second to last one.
Okay, compare the relative condition number of fx x naught given by 2.1. Okay, so in other words, and actually, one thing it's not really a condition number. It's more like an estimate of a condition number. So what I mean is use this formula to get. So what estimate of the condition does that give you compared to what you're getting from the actual case? Okay. Anything more?
Will
Yeah.
you,
Sorry, go ahead.
Oh, Carade?
will you be available to answer questions via email next week?
Oh yeah. I'm still going to be. Yeah, I even got an international data package. I'll be in touch. So
Okay.
yeah. No, I can't be one of those people who goes overseas and shuts himself off. That's never going to happen. I don't care how much it costs me. Yeah.
Okay.
Yeah. Good question though.
On the concept checks, on number 13, I guess I'm a little confused as to exactly what you want to know. That's for 2.4.
Yeah. Oh, okay. I'll point you to one of the examples. Well, like for instance, these last examples where Taylor's polynomials were used to determine a rate of convergence. So how were they used?
Okay.
Yeah. So and so you could like discuss one of the examples for concreteness. That'll help. Okay. Anything else? All right. Okay. Now, alright, so what I want to try in MATLAB is some demonstrations related to floating point arithmetic. Now, you've seen different ways of displaying numbers, like format short, format long, format rat for rational, but there's a different format that's going to be useful to us today, and that is format hex. Now, what does that mean? So, number bases, or bases of number systems that are of interest to us. Of course, we have one we're all used to, decimals, base 10, and then binary, which is what computers tend to use, base 2. So your only digits are 0 and 1. I should mention, back in the 60s, I think it was, there was a computer in Russia that used base 3. I don't know, when we think of binary, 0 is on, 1 is off. I'm not sure what that third digit would be for. I don't know, some middle ground or something or whatever. But apparently, it didn't work well for them because nobody does that anymore. And then we have other bases of interest, like from a computer science world, is octal. That's base 8. So digits 0 through 7. But the one we're going to work with today is hexadecimal. That's base 16. Now, I think, well, how are we going to handle 16 digits when we only have 0 through 9? So you have a digit 0 through 9, and then what you do is the upper lowercase doesn't matter. You use the letters A through F to represent 10 through 15. So A equals 10, B equals 11, and so on up to F. I'll fill those in here. A equals 10, B equals 11, etc. up to F equals 15. Okay. Now, upper lowercase doesn't matter. You're actually going to see lowercase in what I show you here. So if I have format hex, I'm going to show you what the number pi looks like in the hex format. It looks like garbage. You can't make heads or tails of that. But by the time we're done today, you actually will be able to make sense of this. Now, that's not a very good number to start with, but just for fun, I'll do another one, e, that is e to the first, or the exponential of 1. Again, not so informative, although notice the first digit is the same, 4. And that's going to make sense because these numbers, e and pi, are of a similar magnitude. Pi is 3.14, e is 2.71. I found it interesting that, because we always celebrate Pi Day every year, March 14th, but we don't celebrate E Day, which would be February 7th. So, and I'm pointing it out because coming up, February 7th, 2018 is 2.718. So, It's the only E day of our lives. So maybe in this class we'll do something. Okay. Now, so I can start with simpler numbers to give you an idea as to what these hexadecimal digits mean. And the reason why hexadecimal is convenient for us, we really want binary, but MATLAB won't show us binary. But each hexadecimal digit, because 16 is 2 to the 4th, each hex digit maps very nicely to 4 binary digits. So I can easily read binary off of hex, and I'll show you how to do that as well. Okay, so we have like 1 looks like this. If I do 2, and what's happening here is if you look at just the first 3 hex digits here, we have 3FF, 400, and then 401. And these are powers of 2, 2 to the 0, 2 to the first, 2 squared. 3FF, that would be the same as 3 times 16 squared plus 2 times 16 plus, no, not 2, 15, because that's the actual digit, and then 15. So just like with decimal, we'd have like, normally if it's decimal, there'd be 10 to the 0, or like the ones place, 10 to the first, 10 squared. This is 16 to the 0, 16 to the first, 16 squared. And that would be, well, I'll just work that out. I could do this in my head, but I'll probably screw it up. 1023. Whereas if I do 400, well, that would be 4 times 16 squared plus nothing else. And that's going to be 1024. So what's happening is the first part of this has something to do with the exponent. Because what's happening here is the exponent of 2 is increasing by 1 as I go from 1 to 2 to 4. And that's actually what's happening. The first part of this represents the exponent. The rest of it represents like the significant digits in binary. And we don't have any significant digits in binary because these are all exactly powers of 2. So that's why the rest of these are all 0. So what I'm going to do is, first I'm going to dissect these for you. Well, actually, I'll do one more. That's not a power of 2. So 10. So here, this part of the number has something in it, whereas before there was not. So I'm going to have to explain that as well. Okay, so before I deconstruct this for you to show the different parts of a floating point number, I need to show you how to read binary off of hex. So hex to binary. Okay. Now, so for your hex digits, well, the first, okay, well, 0, that's not very interesting. Okay, but now when you have 2, in binary, that's 1, 0, because that's 2 to the first plus 2 to the nothing times 2 to the 0. And then 3 would be 1, 1, 2 to the first plus 2 to the 0. And then 4 would be 2 to the second plus nothing else. So if I go ahead and fill out 5 for you, it's 101. What would 6 be? If we break it down in terms of powers of 2, like here we have 4, here we have 4 plus 1. So how might I express that? What? No, because that's the next power of 2. So that's not, we're not getting at there yet. 110, because it's, the first one is 4, the second one is 2. So we have 2 squared plus 2 to the first plus nothing. Therefore, 7 would be 111, because we're just adding 1 onto that. So another way to think about this is, if I was going to add 1 to this, if you do the usual addition process, where before you would carry if you went over 10. Well, here you carry if you hit 2. So if I add 1 to this, I'm going to get zeros across the board, and I'll get the next power of 2. So 1, 0, 0, 0. And then 9 would be 1, 0, 0, 1. And then 10, which is A, that'd be 1, 0, 1, 0. So what's 11? Take a shot. What? Yeah, 1, 0, 1, 1. Okay, now what would happen if I, now keep in mind, if you write 12 as a sum of powers of 2, what, so if you break it down that way, that gives you an idea of what the digits should be. Well, try your hand at 12. In fact, what you can do is you can add, if you figure out the powers of 2, they're listed here. You can add them that way.
1, 1, 0, 0.
Yes, 1, 1, 0, 0. And then D is 13, so that's 1, 1, 0, 1. So going to odds is easier. So what would E be? Break that down into powers of 2 as a sum. The 14 would be 8 plus 4 plus 2. Yeah, 1, 1, 1, 0. And finally, the last one, F, 15, that's 1, 1, 1, 1. Okay. Now, what we're going to see here is we break it down into a hex digit into binary digits. We'll pad to the left with zeros. And you'll see what I mean when I break these things down. So in other words, so with padding, like 3 would be equal to 0, 0, 1, 1. So the significant digits go to the right. Okay. I probably should have done that from the beginning. Okay. Now, any questions about these? Or how you convert? So it's always, just as a decimal number that it's so second nature to us, is a sum of digits times powers of 10. This is a sum of digits times powers of 2. The mechanism is exactly the same, only with a different base. I remember in elementary school we spent some time on base 5 and like, what on earth are we doing this for? And then we never did anything like that again. Base 2 would have been more useful. Okay. So for instance, 13, 8 plus 4 plus 1, and so on. So the structure of a double precision floating point number, as described in the book, we have 64 bits total, so that's 8 bytes, as opposed to only 4 bytes for single precision. So the first bit is a sign. 0 for positive, 1 for negative. The next 11 bits is the exponent. And that is, it's a number between, I'm referring to it as B, between 0 and 2 to the 11th minus 1, which is equal to 2047. But once you have that, then you subtract 1023 to get the actual exponent. So in other words, the actual exponent is allowed to be positive or negative. So really it could be between minus 1023 and positive 1024. So we can represent both small and large numbers. I should mention, as an aside, just as if I have 5 nines in decimal, well, that's 10 to the 5th minus 1. So similarly, if I have 5 ones, well, that'd be 16 plus 8 plus 4 plus 2 plus 1, which is 31. That is 2 to the 5th minus 1. So if you have a string of 1s in binary, then how many you have, it's 2 to that power minus 1. That's the number that's being represented. So sort of a shortcut in terms of figuring out what the value actually is. And finally, the remaining 52 bits that's the mantissa. So you can think of those as significant digits. and I'll translate that for you as we start looking at specific numbers. So, okay. All right, so I'm in format hex already. So now with this in mind, I'm going to break down 4 for you. So what we have here is, in binary, that would be, 4 is 0, 1, 0, 0. And then we have a 0 hex digit, so that's 4 zeros. And then I have a 1, so that's 0, 0, 0, 1. And then I have a whole bunch of zeros after that. I'm not going to type them all. Now, the first 12 bits, well, that's the sign bit, and then 11 exponent bits. So I'm going to separate them. I'm going to put a slash in here. I use slashes to separate the parts of a floating point number. So sign bit, exponent, mantissa. And what we have here is that mantissa is all 0. So the 0 as a sign bit, that just means it's positive. Now the exponent, well, that would be, we have 11 bits here. This last one to the left, that corresponds to 2 to the 10th. So that's 1024 plus 1. So the value that's represented here is 1025. So the exponent is this value minus 1023. So the exponent is 2. So we get 2 squared, which makes sense because the dang number is 4. Now, the mantissa equals 0, or at least the digits represented here, but we're using normalized floating point numbers. So there's the nice thing about binary is if you acquire normalized numbers, that means the first digit has to be non-zero. There's only one choice. It has to be a 1. So why store it? You're wasting space. So there's an implied 1. So mantissa is actually equal to 1. So a floating point number is, okay, so we have the minus 1 to the sign bit, which is 0, times the exponent part, which is 2 squared, times the mantissa, which is, due to normalization, is equal to 1. So we have 4. Okay. Now, what I'm going to do is I'm going to jump to a slightly more interesting example and see how you're following along. So I put up 10 earlier. Okay. So we need to put this in binary. So that would be a 0 for the sign bit, and then the exponent is 1, 0, 0 because of a 4 that we have here. Then we have 4 zeros because of this 0. And then we have a 2. Okay. And then in the mantissa, we actually have something. We have 4, 0, 1, 0, 0. And then we have a bunch of zeros after that, which I'm not going to bother typing out again. Okay. All right. So, again, the sign bit is 0 because it's positive. The part that's in the exponent, we have 1024 again as 2 to the 10th, plus 2 is 1026. So the exponent is, we subtract 1023, and we get 3, which is 2 to the 8th. Which makes sense that the exponent part gives us 2 to the 8th because our number 8 is the largest power of 2 that is less than 10. Okay, and now for mantissa, what we have here is, now what we have represented by all these is negative powers of 2. So I'm going to throw in the implied 1, and then we have, this first digit is for digit associated with 1/2, but there's nothing. The next digit is 1/4, so we have that in there. And then if we had more digits, we'd have 1/8, 1/16, 1/32, 1/64. So we keep going with negative powers of 2, starting from 2 to the first, all the way to 2 to the minus 52. Are represented here. So we would add those up for whichever one of these had 1s in them to get the mantissa. So that's going to be 5/4. So the number that we have is minus 1 to the 0, because that's the sign bit, times 2 cubed times the mantissa, which is 5/4. So that's going to be 8 times 5/4, which magically equals 10. So we get 8 from the exponent part, which controls the magnitude, and then we have 5/4 from mantissa, which controls the precision. And this 10 is a number that we can represent exactly. Okay. So any questions so far about how these numbers are represented? So you just peel off a first bit. It's always 0, 1 for positive or negative. Next, there's a remainder of the first 3 hex digits. That gives you the exponent. Everything from a 4th hex digit on describes the mantissa. I'll show like a negative number. If I do minus 10, the only thing that changes is the first hex digit. So we have 1 and then 1, 0, 0. So 1, 1, 0, 0 is 12, or C in hex. So because the sign bit is a 1, that's because the number is negative. But the rest of it's the same. The exponent's the same. The mantissa is the same. Okay. Now, there are some numbers of special interest here. There's a command in MATLAB called real max. It's the maximum, it's the largest representable positive number. Now, actually, first I'm going to show it to you in its regular format. Real max. So it's a pretty large number. It's roughly 1.8 times 10 to the 308. But now if I do this in format hex, okay, and what does that look like? So that's a very different kind of number. So it breaks down in binary. We have 0 for the sign bit because it's positive, and then 7 is 111 in binary. And then we have F, which is 1111, and then we have E, which is 1110. So that's the exponent part, and then the rest of it's the mantissa. It's all F's. That's all 1s. Makes sense because it's kind of like, what's the largest number that you get base 10 with a certain number of digits? It's all 9s. You take the largest digit available to you. So all 1s are making a mantissa as large as possible. So what does this mean exactly? The exponent, the number represented here, well, if this was all 1s, it would be 2 to the 11th minus 1. But we're missing this here. So it's actually 2 to the 11th minus 2. Now, 2 to the 11th is 2048, minus 2 is 2046. Yes, I know my power's a 2. I was a computer science major. What do you expect? Therefore, the exponent, you subtract 1023 from it, and you get 1023. So the magnitude of this number is 2 to the 1023. But if I do that now, 2 to the 1023, it's not quite as large as this. Almost. Now, what about this mantissa here? It's all 1s. Well, there's the implied 1, and then there's 1/2 plus 1/4 plus 1/8, and so forth. All the way down to 1 over 2 to the 52. And now the thing is, if you were to add these up, it might be a flashback to Cal 3 in a way. It's like a geometric, it actually is the first part of a geometric series. Because, well, if you were to add these up, if this went off to infinity, what number would you eventually arrive at? You haven't heard the infinitely many mathematicians walk into a bar joke? Yes, it is 2. I must have told this in DE, but okay. No, yeah, infinitely many mathematicians walk into a bar, and the first one orders a beer, the second one orders half a beer, the next one orders a fourth of a beer, an eighth of a beer, and so forth. And then the bartender puts 2 beers in the counter and says, "You guys got to know your limits." So, okay, thank you for the groans. Okay, there's another version of a joke, but that's profane, so I better not do that. Okay, so Yeah, so this is going to be a little less than 2. So it actually turns out to be 2 minus the next term, which is 2 to the minus, so 2 minus 2 to the minus 53. No, actually, no, yeah, 2 to the minus 52, sorry. Okay, so now, so what that would mean is, so if I do 2 times 2 to the 1023 power times that number, 2 minus 2 to the minus 52, compared to real max, that I actually do get the same thing. So that's where that value comes from. Now, what would happen if I went a little bigger? So if I subtract off something less, this number is going to be slightly bigger. Infinity. It cannot represent that number. It's too big. So what does this look like in hex, though? Okay, so this is 0 for the sign bit, and then the exponent is all 1s, and then the mantissa is all 0s. So the exponent is 1 greater than before. It's actually 1023. So even though there's enough bits to support exponents up to, let's see, actually, wait a minute. No, 1024. That's the value. Even though there's enough bits to support an exponent of 1024, you're actually not allowed to use it. So an exponent of 1024 is interpreted by the hardware as infinity. In other words, this is overflow. So once you get past this point of real max, then this is what is actually stored, and it's interpreted as infinity. Now, if I do something similar like 1 over 0, same number, that's also infinity. If I do minus 1 over 0, same thing, except the sign bit is 1 also, to make it negative. So these are other ways to get infinity. What if I do 0 over 0? That's something else. So we have, in binary, that's 1 for the sign bit, all 1s for the exponent. And then we actually have something in the mantissa. There's a 1, and then all of our digits are 0. So in other words, if the exponent equals 1024 and the mantissa is only 1, as in the implied 1, that is infinity. Whereas if the exponent is 1024 and the mantissa is greater than 1, because we have this digit here, that is not a number. In other words, the indeterminate form, which 0 over 0 is. Okay. All right. The other strange thing is, okay, I've shown you the largest representable number. What about the smallest? Now, what's kind of weird is MATLAB kind of lets you down on this one. There's a command called real min. So I do real min. That's the number it gives me. And that would be 2 to the minus 1022. All right. Now, minus 1022 is the smallest allowed exponent. But the thing is, but this is the smallest normalized number that's allowed. So if I look at this in hex, all right, so this is what we have here. So in binary, we have 0 for a sign bit, and then our exponent is 0, 0, 0 from the first 0 here. Then the second 0 is also 0, 0. And then we have a 1, that's 0, 0, 0, 1. And then the mantissa is all zeros. Okay, so what does this mean? So the exponent, what we have here is 1 minus 1023, which is equal to minus 1022. So that's why we have 2 to the minus 1022. But it turns out, so you might think, okay, if I give it a smaller number than this, it should show me 0. Well, let's do that. 2 to the minus 1023, let's say. Oh, that's not 0. Let's go further. Again, not 0. In fact, I can go a lot further. 2 to the minus 1074, non-zero. But if I go one step further, there. So that's the actual for some reason, the command realmin does not take into account denormalized numbers. I don't know why. That's kind of, well, I won't say. Silly on their part. But so now let's take a look at that number. 2 to the minus 1074. Let's see what that looks like. So in binary, so 0 for sign bit, 0 for the exponent. And then the mantissa is, there's nothing there except 1. Okay, so the exponent is 0 minus 1023 is, but this is not an actual exponent. This indicates that the number is not normalized. Now, the mantissa, well, we have 52 bits here. So this number right here is 2 to the minus 52. So the number that's represented is the smallest allowed exponent for normalized numbers, 2 to the minus 1022 times 2 to the minus 52. You add the exponents and you get 2 to the minus 1074. So when you're in denormalized mode, the exponent shows as 0, but the actual effective exponent is 2 to the minus 1022, and then you multiply that by whatever's in the mantissa, where there is not an implied 1. We didn't throw that in this time. So that's where this number comes from. So that's another example of a denormalized number that's just below the normalized limit, 2 to the minus 1023. The exponent is, again, 0. So that's minus 1023. Again, denormalized. So we actually use minus 1022. And then the mantissa is starts with the 8 here. So that's 1, 0, 0, 0, and so on. And that translates into, if you, again, denormalize, so there is not an implied 1, the first bit corresponds to 1/2. So we get 2 to the minus 1022 times 2 to the minus 1, that's 2 to the minus 1023. So that's how that number is represented. So the hardware looks at the exponent and says, oh, there's nothing in the exponent, that means the number is not normalized. So it's the most efficient way for it to check that. Okay. So when you go less than 2 to the minus 1074, that's called underflow. Underflow is not really a big deal. If a number is really small, you just say, oh, it's 0. Because obviously you're not very far off. It's overflow that's kind of a deal breaker. Okay. Now I want to look at actual arithmetic and what happens there. So if I have 10 over 4. Well, now, first of all, 10 can be represented exactly, as we saw earlier. 4 can be represented exactly. Now, what about 10 over 4? Now, that's 2.5. So can that be represented exactly? Kind of looks like it. So in binary, that's going to be 0, 1, 0, 0. Oh, no, okay. 1, 0, 0, 0, 0. So that's the exponent part because of a 4 here. And then the mantissa is 0, 1, 0, 0, and then the rest of it is zeros. Okay, so the exponent, well, what we have here is a 1 in this position. That's 2 to the 10th. So the part that's in here is 1024, but we subtract 1023. So that's 1. and then the mantissa, there's an implied 1, and then we have nothing in the 1/2 place, and then this is the 1/4 place. So 1 plus 1/4. So the number that's represented is 2 to the first times 1 plus 1/4. So that's 2 times 5/4 is 5/2. So sure enough, it was able to represent the result of this exactly. But now, let's flip it around. 4 over 10. So 0.4 or 2/5. That doesn't look so good. Let's see what happens. In binary, so that's 0 for a sign bit, and then we have 0, 1, 1, and then 1, 1, 1, 1 for the F, and then the D is 13, so that's 1, 1, 0, 1. Yep, okay. And then for the, here we have all 9s. Well, 9 in binary is 1, 0, 0, 1, and then 1, 0, 0, 1, and 1, 0, 0, 1. We keep going all the way down to the end, the last 9. And then this A here, that's 10, so that's 1, 0, 1, 0. So this is going to take a little more work to decipher. Now the exponent, well, the B part that's in here, that's, okay, everything up through 2 to the 9th. So 2 to the, okay. So, well, actually, no. I have, if I ignore this 0 here, I think I treat it as a 1. I have 10 ones. So that's 2 to the 10th minus 1. And then I take this out, and I subtract 2. So that's 1024 minus 3 is 1021. Therefore, the exponent is equal to this minus 1023. It's equal to minus 2. Okay. Now, what about the mantissa? That's kind of strange. Mantissa, there's an implied 1, and then this first digit is 1, corresponds to 1/2, and then we have nothing for 1/4, nothing for 1/8. Then we have 1/16, and then we have 1/32, the very next digit. Then we have nothing in 64, nothing in 128, and then we have 256. And then we jump here, and that's 512, and I won't go any further, but that's the pattern. So let's take a look at that number for real. So 2 to the minus 2 times 1 plus 1/2 plus 1/16 plus 1/32. The exact result is supposed to be 0.4. Well, we're pretty close. Now, if I had continued adding, I only got up to here, I'd be closer still. Because if I do 4 out of 10, for all practical purposes, it has the exact result. But it's not really represented exactly. And there's one other thing I want to point out. If this was a pattern, it's kind of like with repeating decimals, only it's repeated binary. If I did the exact result, just like as 1/3 equals 0.3 repeating off to infinity, ideally this should also be 1001. But it's not. And the reason why is, so it equals 1010 due to what's called rounding to even. The number cannot be represented exactly, so it has to round it. And it rounds in such a way that the last digit is even. So in other words, is 0. So that's why that happens. Okay, so even a number, so there are a lot of numbers that cannot be represented. They can be represented exactly in decimal, cannot be represented exactly in binary. Is there any questions about this one? I think one of the explorations where you're picking apart the parts of pi. So hopefully what I'm doing here gives you an idea of how to do that. Now, a very important component of the floating point system is unit round-off, which is the smallest positive number added to 1 in such a way that the result is represented as a number that is greater than 1. So for example, if I do 1 plus like the smallest number I could represent, 2 to the minus 1074, it says it's exactly 1. So adding is to not make a difference. But if I pick a larger number, but still pretty small, like 2 to the minus 40, let's say, well, here we have something non-zero. So there is a command called EPS that gives that unit round off, and that's actually 2 to the minus 52. So if I do 1 plus 2 to the minus 52, this means it's something that is slightly greater than 1. If I look at this in hex, so the exponent turns out to be 0, but the mantissa has a 1 in the very last position. That corresponds to the 2 to the minus 52. So the mantissa equals the implied 1 plus 2 to the minus 52. So let's suppose I take a number that's a little bit smaller, 2 to the minus 53. That's this is too small. So that is so this result is considered exactly 1. So, but here's the funny part. Let's try a number that's in between these two. 1 plus 2 to the minus 52. 2 to the minus 53 plus 2 to the minus 54, let's say. Well, that is greater than 1. If I look at it in hex, now it's rounded to 2 to the minus 52. So that's why we actually get something here, because this is large enough to round to round up. Now I could keep going, and it'll still round to the same result. Now, one of the explorations, I think, I don't remember if I actually went with it. You could keep playing around with this to see what is the smallest number. Like if I keep decreasing this second power of 2, what can I get away with? So it still rounds to 2 to the minus 52. So that's why MATLAB labels this as the machine precision. But you get the idea here that if you can add anything here that happens to round to 2 to the minus 52. All right. Although what's kind of weird is, and this is something I have to look up, I'm not sure why it did not round to even in this case. And the last digit is a 1. That's odd. So, well, odd in two senses. So, okay. Now, at the end of the section, there's a discussion of issues that can happen with floating point arithmetic. So I'll give you an example of that. I'm going to choose x to be really large. Like, well, the largest I can get away with is like on the order of 10 to the 308th power. I don't want to go back quite that big. Let's say 10 to the 200th power. Okay. Now I'll just make y equal to something. I don't really care. So if I do square root of x squared plus y squared, infinity. Even though this number, square root of x squared plus y squared, y is very, very small by comparison, plus y squared is only slightly greater than x. Therefore, it ought to be representable. Well, it is representable, but not if you compute it this way. So one of the explorations is figure out why. What is it about this process of computing square root of x squared plus y squared that causes a problem? And more importantly, what can you do about it? How can you algebraically manipulate this formula, so this is something you work out on paper, and then you can try it out in here, to ensure that as long as x, y, and the result are representable in the floating point system, then you can actually obtain that result. So that's one big issue with floating point arithmetic. Another is catastrophic cancellation. Now, what I'm going to do is I'm going to construct a quadratic equation for coefficients a, b, and c. Now, a and c I'm just going to set equal to 1. B I'm going to set to a nice large number, let's say 2 to the 100th. Okay. Now, what I can do is compute the two roots using the quadratic formula. So we have b plus square root of b squared minus 4 times a times c all over 2a. Okay, and we get 0 as a root. Now, the equation is x squared plus 2 to the 100th x plus 1 is equal to 0. So if you take this root and plug this into this equation, it's definitely not going to satisfy it, because you're going to get a contradiction of 1 equals 0. What about the other root, x 2? If I just choose the minus sign in the quadratic formula, and we get a pretty large number. Okay. And if I go ahead and substitute that into the equation, so that would be a times x2 squared plus b times x2 plus c. Well, on the one hand, I got 1 again. But I should mention that this is still actually supposed to be, this is very accurately one of the roots. This one is not. And the thing is, because this is such a large number, it's still going to be rounding error. So, and the thing is, this error here of getting 1 is still really small compared to the values that we're plugging in here. But at the same time, what also happened was, in plugging x2 into the equation to get this 1, and also using a quadratic formula for this root x1, both are susceptible to cancellation error. And the reason why is you're subtracting large numbers that are very close to one another. So in this case, up here, because a and c are so much smaller than b squared, then what we have here is this number here, square root of b squared minus 4ac, is essentially equal to b. There's very little difference between them. So then we have minus b plus b, essentially. Any difference between them is lost due to round-off error. And that's why the result is represented as exactly 0. Similar thing going on here. If I have this value here is, actually if you compare this to my b up here, they're exactly the same except for the sign. So again, here, or at least to the digits that we can see. So here we have cancellation error again. The result is supposed to be minus 1. But because the numbers that are subtracted are so much larger, it ends up not being what we get. So that's unfortunate. So we have, so these are kind of things that happen. And that's why in one of the explorations in this part, you do some algebraic manipulation that you've done before in expressions involving square roots to come up with a different quadratic formula that kind of looks like the one you're familiar with, but what it'll do is, because this root is fine, the numbers that we're adding here are the same sign. There's no cancellation issue with this root, but there is with this one. So by manipulating the quadratic formula, you actually get a situation where this subtraction ends up becoming an addition. So that way you can use the regular quadratic formula for one root, this new quadratic formula for the other root, and therefore both roots can be computed without performing subtraction. And that is what MATLAB does. If you're using the roots function to compute the roots of a quadratic equation, then you then what happens is you get at least to the limits of floating point system, you get the correct values. Now, as I showed an example before of roots and poly, like where we got complex numbers and we expected real roots, it's still not foolproof. And some problems, and the numerical methods can help you solve a lot more problems than the analytical methods can, but there are still limits, unfortunately. Okay, so so now I have an idea as to how floating point numbers are represented. So, are there any questions at this point? Okay, yeah, my brain's pretty fried too. But all right, so so this is really all. That this is the end of the coverage of chapter 2. So now you can, well, 1/3 of you still need to get homework 1 finished, please. Not that I'm anxious to grade them by any means, but I do need to do that for the 14 of you who have turned it in. Again, please reach out to me if you're having difficulty, or whether it's with the problems themselves or just something has come up that's made it difficult to complete. It's better to be, and this is one thing that students in general need to learn, it's generally better to take the path of being more communicative rather than less about these things. So I hope to hear from you one way or another, either with the assignment completed and turned in, or let me know what's causing trouble with it, so that you can move on to chapter 2. Now, on the site, I meant to mention this earlier. When I did the LaTeX document last time, I posted that here. So if I do something in class that's not in a diary, it's not in a textbook, I'll put it here on the examples page. And actually, what I'll do a little later is, like after class, is I'll put up the .tex file also. So if you want to learn LaTeX, you have a sample to start working with. Alrighty. Okay, then homework 2 is here, waiting for you to get cracking on. Well, a couple of you have already. And then I'll be posting the problems for homework 3. It's on chapter 6, just because Dr. Chen's going to start chapter 6 next week, but that's not due for nearly a month, so you don't have to think about that right now. But there's no time to fall behind. Okay. All right. So I will see you, well, in 12 days. But I hope to hear from you sooner than that.